Good day, everyone. Good day, sir. We are the Group 5 and we are tasked to discuss about the radar plotting. But before we start, I am the Cadet Jan Simon Hava together with Cadet Ibarita Kaisarom, Cadet Habadan Dave, and Cadet Humawan Aldrin. So, the, the intended learning outcomes. So, at the end of the session, the students shall be able to define on how the marine radar works, familiarize the basic components of marine radar, determine the radar errors, and perform manual plotting techniques given the information from the radar observation. So, how does marine radar works? So, the term radar is an acronym for radio detection and ranging. The marine radar works on the basic principle of electromagnetic waves. The radar antenna sends the high-speed electromagnetic waves to establish the location, which is the distance, the velocity, and the direction the wave traveled along with the altitude of the object, moving or stationary. So, as you can see, this is the actual look in the ship. So, let us understand how does the marine radar works. So the radar system out electromagnetic waves as a high-speed signal which will travel several miles in the direction of radar facing. If there are no objects in the direction of the wave, the radar screen will show blank. If there is an object which will reflect the wave back to the radar, the computer setup of the radar will determine the distance between the ship and the object along with its location. Hence, it can be said that the radar basically reads two things. So, the position of the object and the direction of the same. So, position of the object. The radar antenna is continuously rotating on top of the ship, sending and receiving signals. Hence, the radar is sweeping the signals all around the ship. As the radar pulse waves are reflected by an object, it will travel in the same direction and will be received by the radar detecting the position of the object. When the pulses are received back, the computer screen will log the position.
Good day, sir. I'm the Cadet Kaisarom Ibarita. The shown image is how ships can receive signals and output signals and can radar rotating at high speed. So, distance from the ship, as the radar antenna is constantly sending and receiving signals from the object in the way of the electromagnetic signals. The received signal is sent back to the computer unit, which calculate the time taken for the signal to reflect back to the radar. Once the computer knows that time, it will calculate the distance by using the speed and time formula. So, this is the marine radar diagram. As you can see, this is the basic components of marine radar are shown in the below diagram. As you can see the antenna which produce electromagnetic waves to the objects, and waveguide. There are transmitter, duplexer, receiver, modulator, master clock, signal processors, and radar screen. What are the possible health effects of radar? Most studies conducted to the date examine health effects other than cancer that prove into psychological and thermoregulatory responses, behavioral changes and effects such as inductions of lens, opacities, cataracts, and adverse reproductive outcome, following acute exposure to relative high levels of RF fields that there are also a number of studies that report non-thermal effects where no appreciable rise in temperature can be measured. Uses of marine radar. Number 1, to calculate range and bearing of the target, and thereafter use the information to determine the speed, course, etc. 2. Integration with other shipboard equipment such as ICDIS to derive precise data. 3. Navigating own vessels and her course with regards to collision avoidance. 4. Fixing the ship position using terrestrial objects such as lighthouse, buoys, etc. 5. Differentiating between targets in high traffic density areas. 6 is determination of the weather to an extent. 7. Use by BTS in controlling coastal traffic. 8. Usage of features such as parallel indexing to ensure safe navigation. 9. Alleviating workload on the OOW or officer and watch on the bridge. 10. Used extensively in pilot and covers the above aspect.
So hi, this is Decadent Dave Habadan. So here are the continuation of our discussion. So cancer-related studies, many epidemiological studies have addressed possible links between exposure to RF and excess risk of cancer. However, because of differences in the design and execution of these studies, their results are difficult to interpret. A number of national and international peer review groups have concluded that there is no clear evidence of links between RF exposure and excess risk of cancer. WHO or World Health Organization also concluded that there is no convincing scientific evidence that exposure to RF shortens the lifespan of humans, or the RF is an inducer or promoter of cancer. However, further studies are necessary. So this is the illustration of the skin cancer. As you can see, there are some mm, rashes on his hand. Next is the radar errors. So first is the heading marker alignment. Second, the EBL not alignment. Third, the gyro input with error. Fourth, the improper tuning. Fifth, improper range. Sixth, the blind sector. 7. The adjustment brain clutter or set clutter. 8. The own vessel's date input error. 9. The range and bearing discrimination. 10th, the beam with distortion. 11th, side lobe echo. 12th, the multiple echo. And 13th, the second trace echo. So one of the limitations of ship radar is that it may not be able to detect an object due to its size, proximity to sea surface, when the object is a poor radar target because of its construction or design. For example, the military ships are designed so that radar waves do not reflect back to the receiving unit of radar scanner. This also happens with wooden fishing boats as they have poor radar reflective surface. So small unit boats engaged in fishing are also difficult to sight visually at night. Sometimes they may not be seen during daytime from the bridge due to height or the angle of viewing or reflection of the sea surface. When navigating in the proximity of such vessels or their own operating areas, it is good practice to post alert lookout with a walkie-talkie on the forecastle deck. So this is the illustration of a lookout on the forecastle is closer to sea surface and has a better chance of sighting small crafts. So as you can see in this illustration. So next,
Hi, I'm Aldrin Namawan. So, in the following picture, seaweed is giving very good radar returns due to the highly reflective surface. It had covered the whole sea surface during low water. Because it was the ship's first call to a port area, which was not surveyed. My first thought was that there may be an error in the chart and we altered course to stay well clear. We started approaching only after getting positive confirmation by all possible means that it was safe to do so, and there was ample water with sufficient depth. It is always better to be safe than sorry. It was also concerned if the seaweed, because of being so densely packed, could could in any way fall the bow thruster. So next is, in this picture, you can see the example that the vessel is very close to the shoreline. So sabatable naman is siya diri na part. So about radar. So next is radar ARPA performance standard. So in this chart, you can see the example of the radar ARPA performance standard. So size of ship craft, minimum operation display area diameter, minimum display area, auto acquisition of targets, minimum acquired radar target capacity, minimum activated AIS target capacity, minimum sleeping AIS target capacity, and trial maneuver. So, next is the requirement contained in the table should be met as specified for X band and S band equipment. So, as you can see, there is the target description, target feature, and detection range in NM. Detection range experience and practice will be affected by various factors including atmospheric condition, evaporation duct, target speed and aspect target, materials and target structure. These and other factors may either enhance or degrade the detection range stated, as ranges between the first detection of on-ship that radar return may be reduced or enhanced by signal multipath, which depend on factors such as antenna, target, centroid height, target structure, sea state, and radar frequency band. IMO Revised Performance Standard for Radar Reflection, Resolution MCS 16878 Radar Cross Section RCS 7.5 M2 for X band, 0.52 for S band. The corner reflection used for measurement is taken as 10 m squared for X band and 1 m squared for S band. The typical navigation buoy is taken as 5.0 m for X band and 0.5 m2 for S band. For typical channel marker with an RCS of 1.0 m2 X band and 1 m squared per S band, and the height of 1 meter and detection range of 2.0 and 1 m respectively. RSC for 10 m small vessel taken as 2.5 m squared for X band and 1.4 m squared for S band taken as a complex target. So that's all. Thank you.